Great. So welcome everybody to the, I think, 9th webinar in the HPCP webinar series. And today we'll be talking about predicting outcomes of behavior change interventions, my favorite topic. So I'm Professor Jana Hastings at the University of Zurich and St. Gallen, and I'm joined today by Professor Robert West. And Robert, I'll let you introduce yourself quickly.
Yep, thank you. I'm a Professor Emeritus of Health Psychology at University College London, and a lot of my work has been in smoking, and since smoking is the use case here, I was able to provide some of the expertise that helped the project on that.
Great. So what we will do today for this webinar is we're going to have around a 20 minutes long pre-recorded presentation, which we prepared in advance. So this will play through. We'll still be here, but then we will come back on live for a live discussion straight afterwards. And we are really looking forward to your questions. So while you're watching the webinar and at any point afterwards, please put your questions into the Q&A box, which you should find at the bottom of your Zoom screen. And if you see questions that other people have put, click on the little thumbs up next to the question. So this will tell us which questions are most interesting to everybody, and we try to answer questions in that order. We might not get to all of the questions during the session, depending how many you ask. If we don't manage to get to all the questions, we will nevertheless answer them offline afterwards. So all questions asked together with answers and answers to questions we didn't get to during the session will be shared on the Open Science Framework. This webinar and all of the webinars are being recorded, and the recordings are also being uploaded to YouTube afterwards, as well as slides shared on the Open Science Framework. I hope that's useful if you need to share it with colleagues who were not able to attend. Right, so without further ado, let's get on with our exciting agenda.
Today we're looking at the prediction system, the algorithms that we've developed to predict outcomes, in this case smoking cessation outcomes, from the data in the Human Behaviour Change project. And I'm going to be joined by Jana Hastings, and the two of us are going to go through this together. And the way it's going to work is that, first of all, Jana's going to ask me some questions about the setup of the prediction system, and then I will ask her some questions about the technicalities of how the prediction system operates. And then we'll just provide a short demonstration. Before we do that, I just want to show how the prediction system fits into the overall structure of the Human Behaviour Change project. What you can see from this slide is that what we have in the Human Behaviour Change project is the Behaviour Change Intervention Ontology, which provides the overall structural organisation of the information that is being dealt with here. That informs the information extraction part of the Human Behaviour Change project, which is done manually and which we aimed to train computers to do. That information extraction then leads to data that we can use for outcome prediction, and also for exploring studies in more depth. And we also have a system for finding studies in the first place. And the information organizational part of it informs the paper authoring tool, which you're going to hear about in a later webinar. Okay, so Jana's now going to ask me the first question, and I'm sure it will be a very penetrating one.
So my first question is, why is it that we're building a prediction system? Why prediction? I mean, normally when people look at studies and they read the study and get the results of the study, and even when they put multiple studies together and do an analysis based on multiple studies, they don't do predictions.
The reason we built a prediction system is because that's actually the thing that researchers and policymakers and practitioners need directly. What we have at the moment in the field of research is something that sort of gets you quite a long way there, but it's not the final thing that you need. And you actually have to do a lot of guesswork to go from the data that exists in the world and that's been synthesized to what you need. So let me explain that a little bit better. What we have in the data and the literature at the moment are individual studies, and these are pulled together in what are known as meta-analysis and meta-regression studies. And they combine data from individual studies to make generalizations about the findings from those studies. And that's the key. The first key thing here is that our existing statistical techniques for combining data from different studies make generalizations about the findings that existed in those studies in their own contexts and so on. They do not directly make predictions about what would happen in a new study or in a new scenario in which we might find ourselves, even though it may involve essentially the same intervention. So that's the first thing. Meta-analysis and meta-regressions are effectively descriptive ways of making generalizations about existing data sets. The second thing is that the existing studies always are looking at comparative outcomes, them taking advantage of the fact that we have randomized controlled trials in which the randomization process effectively is intended to equalize all the uncontrolled and uncontrollable parameters that may influence the outcome. And so what you get out of them is some kind of effect size, which could be a difference in the mean of something like mean alcohol consumption, or what's known as a rate ratio or risk ratio, which is the percent to which one intervention results in an outcome such as smoking cessation compared with another, or an odds ratio. Those are the classic ones. So we have effect sizes, and that's fine. That's very useful to know what the effect size is of a given type of intervention versus another. But it doesn't lead you directly to a prediction of what the outcome will be, particularly in a new scenario. And the reason for that is that you haven't incorporated information about the population and so on that would allow you to make a prediction of what the outcome would be. So now prediction, it turns out, is actually much more challenging as a task than explaining an existing data set. It's worth it though, because it provides a much more robust test of the model that you're constructing. It's much easier to find parameters that explain existing data than it is to predict outcomes in new data, in new cases. Let's just take the example, an example from smoking cessation. There are a number of meta-analyses of, for example, what's known as digital aids for smoking cessation, and these can show an average rate ratio compared with whatever the controls are, often nothing at all, or printed materials or something like that, varying depending on the meta-analysis between 1 and 1.5. What does that tell you? That shows that the digital interventions can be maybe up to 50% more effective than whatever the control was in terms of the smoking cessation outcome. But there's lots of variability, and there's lots of variability actually in the conclusions that are drawn by different meta-analyses, depending on what studies go into the meta-analysis and what the contexts are, but also what the digital aids are. A digital aid is a very, very broad definition, which can include lots of different things. Now, at the same time, you see, for example, meta-analyses of nicotine replacement therapies for smoking cessation showing an average rate ratio of around 1.6, about a 60% increase. Unfortunately, neither of these tells us what outcomes we can expect. What percentage of the population who get a given intervention would be expected to stop smoking for, let's say, 6 months? in a new scenario with a new context. And this is really important, because that's actually what we need to know. We need to know going forward. Okay, you've got all this data going forward. What's our best prediction of what's going to happen in the future in terms of the outcome? So they only provide a broad summary of what was found in the context in which they were examined. And so what we've tried to do with our prediction system is to create a system which goes beyond that and actually directly predicts what we think will happen using the information from the randomized trials. And we do that using machine learning techniques that Jana is now going to explain. So Jana, over to you. Tell us about the prediction system and how it actually works.
I think the basic idea of an artificial intelligence prediction system based on data is that you stick the data in one end and you stick these sort of desired outputs, which are coming from what you've already observed. And then you do the learning process in which the model tries to get better and better at getting the correct output based on the input it's got, right? So it's machine learning in which there's a training phase where the model tries to learn the right internal parameters and construction in order to make good predictions. And of course, then in order to test whether it has worked or not, you need more data in order to sort of apply what the model has learned and then check afterwards. So what we do is we split up the data set into a training set and a testing set so that we can do the training where it sees the output and then make the prediction afterwards with the trained model and see how good it's done. So that's the basic overview of machine learning in general. What we did in particular was we tried to build a system that was interpretable while still being trainable using the best modern machine learning technology for fitting the data. So this was an important objective because interpretability seems to be really essential in order for such a system to be used in any kind of real-world decision-making context. It's important to always have a transparent trace from the input variables, features, to the prediction, and how much of an impact each input variable or feature had on the prediction in a given scenario, right? So that you can use this to support decision making. So we worked with a system where the features, which were coded up using the behavior change intervention ontology, supplemented with a few extra ones, and the features and their relationships kind of went in as part of the information available to the model, as well as the data, like the numbers, the values for ages, and so on. And then the system learned relationships between features or combinations of features and parts of or impacts on the outcome value. Right? So our outcome values are percentages of smoking cessation, and our system learns small pieces of prediction, which when taken all together result in a total prediction of an outcome for a given scenario.
So that's the basics of how the system was constructed. Now let's see it in action. So this is what the current prototype of the prediction system looks like. And you'll see here are things that you can set around what we might call the context and the methodologies around the study, which are things like mean age, which you could set to 50 or lower or higher. Every time you change one of those, then the outcome will change. Mean number of cigarettes per day or times tobacco is used, if the person's a patient or not, the proportion female, whether it's continuous abstinence or point prevalence, whether there's biochemical verification or not, and what the follow-up is at here we've got 52 weeks. So that sets your sort of your control rate, as it were, which is then displayed here. And these are the rules that the system has come up with, which you can't read because they're very small writing. But in the system itself, it will be a bit clearer when it's on your screen. Here in these bars, you can see how far those rules have either taken the overall rate down versus up. And for 52 weeks with biochemical verification, continuous abstinence of people, a population smoking an average of 10 cigarettes per day, mean age 50 and 50% female, you can see that it would predict, if you don't do anything, in a control group of an intervention, you'd end up with somewhere between 1 and 2% stopping smoking, which might seem very low to you, but remember that this is our projection of a sort of completely inactive control. It's not just what people have designated a control condition. It's actually a control condition in which the kind of people who go into smoking cessation trials would get if they received nothing at all. Literally nothing, no behaviour change intervention at all, which hardly any control conditions are. So this is what you might call a sort of a genuine control, or a sort of hypothetical zero control. And then what you could do is, on the left-hand side here, is that you can start to add things in the intervention and see what happens. So let's, for example, add pharmacological support. When you do that, it offers you options about what kind of pharmacological support it's going to be, and we've ticked varenicline there, and we can see, okay, well, what's going on in the intervention here? With just varenicline and no other behaviour change techniques used, no support of any kind, which never exists, there's no such trial, but if there were such a trial, this is what we'd predict, that you'd probably bump that up to about 7%. Success at 52 weeks, which makes actually quite a bit of sense to me anyway, as a expert in smoking cessation, because most of the kind of pharmacological supports that we've got would need some kind of support in order to get maximum benefit from them, and the behavioural support adds value to that as well. So, okay, that's fine. We've got pharmacological support and it's varenicline. Let's see if we can do any better than that by adding some further BCTs in relation to the behavioural support part of the intervention. Let's add problem solving here. Now you can see that problem solving on its own has a little bit of effect. Let's put in social support unspecified. Well, that bumps it up quite a bit. So now we're getting up to 9%. Now, what we haven't done at this stage is to say what kind of delivery we're going to be working from. So let's say, well, so as far as the system's concerned, when it's making its prediction at the moment, it doesn't know whether this is going to be at a distance, or is it going to be face-to-face, or what kind of thing it is. So let's tell it now specifically that it's going to be face-to-face. And here you can see that it's bumped it up some more. So you're now getting something like almost between 11 and 12% success rate with a couple of BCTs delivered face-to-face with varenicline. We also haven't told it at this stage what kind of a source we've got here. Who's delivering this? Does it make a difference whether it's a health professional, which would be a doctor or a nurse, or a psychologist? So let's say that it's a health professional, for example. And you can say that bumps it up a little bit more. So now it's got some more information to go on. It'll tell you a little bit more, and probably more accurately, what you can expect to see. So you can see how you can build a scenario here in which you try adding or removing various BCTs, different types of pharmacotherapy and so on, and you can look to see the impact that that's going to have on the overall success rates. And you can see that with all that, you're boosting the success rates, boosting them by more than 10% in this particular sample of smokers. Now, what if the sample of smokers was, let's say this were people who are a bit older? You can get it up to about 14%. What about if it's young folks who we know don't start smoking very much. Well, you can see now it's actually gone down quite a bit, the overall success rate, because we know that young people are less likely to quit smoking and so on. And that's continuous abstinence. If you go to point prevalence, which is just whether they were smoking usually in the last week of follow-up, you can see that typically the rates are a bit higher for reasons that you can imagine. So you can, when we've produced this, and on June the 6th this will become live and you can mess around with it to your heart's content, you can see that what we're doing for the very first time ever, as far as I'm aware, in the field of smoking cessation, is to provide a tool which uses the data from, in our case, more than 500 studies and over 1,000 study arms, to provide actually direct predictions as to what we think, or what the studies suggest the outcomes are going to be. And you can compare that with various types of intervention and what the situation would be like if you didn't do anything in that kind of study population. So to summarize what we've covered here, first of all, I think the prediction system goes an important step further than existing meta-analysis and meta-regressions in attempting to predict what outcomes would be in new scenarios, rather than estimating the average difference between an intervention and comparator in an existing set of studies. And this is a much more challenging task, but it's also more useful. Secondly, the prediction system uses a large number of features from around 500 studies and around 1,000 study arms to make predictions using an interpretable machine learning system that's been trained on a training set and then tested on unseen study data. Thirdly, the interface allows users to specify important features of the study population and then add and remove intervention components, including content and delivery components, to obtain predictions as to what the outcomes will be based on the data available. And then fourthly, an important caveat around this is, of course, the predictions will only ever be as good as the input data allows. And one of the things we've discovered in the course of the Human Behaviour Change project is that really huge amounts of important data are either missing from study reports or presented in a way which doesn't allow them to be used. And that's something that we really need to correct going forward. And finally, I think we can regard this perhaps as the beginning of a new phase of behavioural research in which studies are conducted and reported and the evidence synthesised in a way that allows ever-improving models to be created and predictions made.
What a fantastic vision to end off with. This is really good. And we have lots of questions that have already come into the box, Robert. So I think we'll just start at the top. So our first question by MS is, what is the expected prediction accuracy, particularly assuming you don't have microdata to build predictions and there may be only a small number of studies having each specific predictive feature, such as intervention modalities? So I'll start, and perhaps you can add something. If that's all right? I'm taking my chair's privilege there, Robert. So we did remove features from the data set, so intervention types, if they had less than 20 appearances in the data set. And we sort of empirically determined this as a point at which we could not learn anything useful for that feature because it was too sparsely represented. Then for the ones that remained, so they were having at least, but it's still the case that it's a kind of small and sparse data set, and the learning is not perfect. So our expected prediction accuracy is not so great. So I don't know, Robert, what do you want to add some thoughts to this troubled question?
Yeah, no, I think this is really the critical thing is how close do we get? And I think what we'll see going forward is as we as new study, and since this data set was finished, I think there's probably been about at least 50 new studies, perhaps 100 new studies being done, because they're coming in thick and fast. And I think that we will be able to see really how well this prediction is going. But the really important thing about this is that we'll be able to retrain the model, and we'll be able to. It's something where you don't just sort of find out what your prediction accuracy is, and then if it, whatever it's doing, and if it doesn't work, it doesn't work. It's using machine learning, you can always improve it. So this is like base camp for the model. One of the things that you see, or I found doing a sort of a simple regression model, which is a somewhat different kind of thing with this data set, was that if you did what's known as a random effects model, this will mean something to some of you, but essentially a random effects model is one in which you take the study as a unit, and you can say, okay, in that study, we've got an intervention arm and a control arm, maybe two intervention arms. But if you take this, if you can incorporate what the outcome is for the study as a whole, you can get really accurate prediction, sort of within 2 or 3 percentage points. But as soon as you don't allow yourself to get the benefit of the fact that you've got, what the study figures are, then prediction is much, much harder. What that tells us is that even with all the information we've got, we're still missing a lot of crucial information. And any of you who are familiar with smoking cessation will notice that we don't, for example, have information on the level of cigarette dependence, which is a big predictor. And the reason for that is because it's measured in too many different ways. And this is another example. How frustrating is it that you've got potentially important data that's measured so variably that you can't use it adequately in machine learning models? So it's a great question. And the answer is, I think that you could see for yourself that the predictions it's making are pretty close, I would say, to what you'd expect. That's quite good. They can definitely be improved. There's a long way to go. One other thing I should say is that, as has been pointed out by my colleague Marijn de Bruin in his work, that we're using the study reports, and the study reports actually have only very limited information on what was in the interventions. So, the failure to report enough information is a limitation. So that all needs to be improved. And as it is improved, we will get better predictions.
That's right. So just to have a sort of sense of how good or bad the predictions are, I think we're looking at the moment at a sort of average error of about 9%. For the study data, but this is heavily impacted by some rather unexpectedly large studies, which, by large, I mean showing a large effect, kind of more than we think they should. And this potentially reflects problems with our literature, right? If you have, I mean, it's not necessarily the case that all studies are equal.
You typically, if you've got let's say you've got a study of only 50 people, and by chance it gets, 60% success rate, that's going to skew the data. So
because it's atypical.
Yeah.
So we have some sort of follow-on questions on this one. So one is not only accuracy, but also level of uncertainty of point predictions. So this we're not estimating with the current method. I think basically the average error is estimated for the model as a whole, but not for a specific prediction with this method. So yeah. I think in the future, we may explore kind of sampling approaches which let us estimate this, but for the moment, we don't have this information. And then the next sub-question.
Before we just go on to that one, I just want to add one other thing, general point, which is this data set that we're using is completely open source and available on GitHub and available to any statistician, computer scientist, or interested person to see if they could do a better job. And I hope and it would expect that, you know, if people put their very brilliant minds to it, that they might be able to come up with a better system.
Yeah, that's right. We are really happy to invite alternative approaches to try out on the same data, and kind of, I think this is one really exciting aspect about working in an open source way, and then you have the opportunity to benefit from the hive mind of great people who work on these types of things, right? This is really exciting. So the last sub-question of this first question is, you can be adjusting the model to improve accuracy. So I think this is kind of what the training process is doing, right? So we train in several iterations where the model has access to both the outcomes and the input settings, and it learns its internal parameters iteratively. And then after that, we test it on a subset, which it never saw. So yes. So moving on to the next question, and for something completely different. Isn't there an argument that you can never predict behavior as it is so dependent on context, and also on the quality of papers that a system has been trained on? Robert, I think this is one for you.
Yes, the answer is it's not black and white. It's always a question of how much. I mean, we obviously do predict behavior, and this system does predict it to a degree, and that prediction can always be improved. I always think of behavioral science as much more like meteorology than mechanics. Or more, perhaps even more like quantum physics than Newtonian physics. You know, human behavior is subject to, you know, huge numbers of unmeasurable influences. Even if you had the perfect model of a human, there's so many unknowns in any given situation that there's always going to be a level of indeterminacy in terms of your predictions. And of course, and thank goodness for that. So you can, in fact, I actually think that humans may have even evolved to be a bit unpredictable, because if we were completely predictable, it would be the end of us.
I actually know somebody who's proven that point, exactly that point, in some model organism or other. So proven that there is selection for unpredictability.
Oh, that's really good. I must get that for an article I'm writing, because it makes sense, of course. So yes, but on the other hand, obviously we do want to be able to predict certain things to a degree, if we're developing interventions to try and influence behavior, like help people stop smoking or promote behaviors to prevent climate change and so on. So it's always a matter of degree, I think, and always a question of how far can you go. But you also, I think, absolutely raise the point of the quality of the data. And this has been what's perhaps the most shocking thing to me over the last 6 years, as someone who's been an editor of a journal and done a very large number of randomized trials myself. Really shocking, you know, wow. we're sort of really a proto-science rather than a science, because we're not using, you know, doing it with the level of rigor that you would expect. Now that will change, and I think part of the legacy of the Human Behavior Change Project and what follows will be a change in the way that we report our studies. Yeah.
I just want to come back to this really interesting point that you made, Robert, about the prediction. I think our objective is not necessarily to predict an individual person's outcome, right? It's more about predicting average responses to a particular intervention given a certain context, And this is a really important thing to know if you want to recommend interventions, right? You sort of want to know which one will work better, what's the average effect you could expect for a certain combination of interventions in a certain context. And this information is kind of missing at the moment, right? There is no clear way to answer those questions at the moment. Would you agree with that?
I do agree. We don't have a methodology. I mean, the holy grail, ever since I've been working in smoking cessation, and you see this with mental health and with other behavior change interventions, is how do you optimize an intervention for a particular group in a particular context, etc.
Yeah.
And we haven't been able to do that, is the truth of the matter. And I think partly because we haven't had the methodology. I think with this type of model, we can now start to at least get the data that would enable us to help to do that. But I also think there are occasions when you want to predict individual behavior and help individuals, you know, if you're running counseling sessions. But the Human Behavior Change Project is not about that. The Human Behavior Change Project is about predicting the outcome of interventions on populations. Yeah,
really good point. Okay, great. So we'll move on. Thanks, Michelle S., for the really great question. We'll move on to our next question on the list, which is by MS again. Does the model take into account interactions between different features, especially in showing the impact of each feature as regard the final prediction? So yes, the model is able to learn interactions. So we are able to induce, so we learn the most predictive, the training process spits out the most predictive combinations of features and single feature kind of weights. And then these are added up all together in order to make the final prediction. But it's only able at the moment to induce kind of binary interactions and combinations, linear combinations of those and such like. It's somewhere in between a really simple model and a really complex model, and we're not able to use the full potential complexity that some other models might have, but we keep the feature that you could look at what the system has learned directly. So this is what we mean when we say the model is interpretable. And when you saw the demonstration earlier, you could see exactly the rules that were used to make the prediction are also displayed as a kind of explanation of a specific prediction. Robert, do you have any thoughts about that?
Only that I think that as once you get beyond simple additive models into anything interactional, obviously the number of parameters just explodes. And you very rapidly get to a point where you've got a model that's over parameterized. So it can do a fantastic job at explaining. This is something I was referring to earlier. You could do a really, really super job at explaining a data set and actually a very poor job at predicting any new data because it's overfitted to that data set. And it's always a question of trying to get the best compromise when you're trying to do that. And for those of you who are not familiar with it, I can highly recommend a fantastic book by Gert Gigerenzer. I think it's called Being Smart in a Smart World, which talks about this issue and about how very often in unstable in situations with high levels of complexity, actually, you're often better with simpler models. They do a better job at predicting particularly in an explicable way that you can use what's going to happen in the future. And that, to some degree, machine learning models have rather in the past erred on the side of explanation, doing a super job at explaining stable systems, but not worked terribly well when it comes to predicting new environments. Gert Gigerenzer's book, he's a fantastic psychologist, and it's a very good read, and it explains this amongst many other things very well.
Yeah, that was a really good read, Robert. I was really glad that you recommended it to me some time back. I just had another thought about this, which was this idea of sort of actionable predictions, that you sort of need to see what the prediction is in order to take action about it. And that reminded me that this necessitates a kind of transparent and somewhat simpler model, because you can't, if you have too many parameters, you can't follow, right, what's going on. And this reminded me of an interesting finding in machine learning image processing research, where they found that the bigger the model, so we're seeing obviously really good results with really large models, but a recent finding I saw was that the bigger the model, the more it diverged from the sort of human strategies for image recognition. And this obviously then questions whether the performance of the model will generalize to other situations outside of the training sample data set. I just thought I'd add this really interesting finding. So we need to, in this age of machine learning, also get really good at understanding what humans are doing. That's what I come back to again and again. Right. So the next question, how transparent is the predictive system? So this particular system, which we developed a kind of custom system for this problem, it's completely transparent in some sense, because you can see all the parameters in terms of the features. I don't know, do you have anything to add to this?
No, it's if the text was a bit more readable, it'd be a bit more transparent.
Yes. So, notwithstanding, unfortunately, interface constraints, which it would be nice to. So presentation is always a really hard problem, I think. And sometimes there's no, I mean, you can spend years just developing a good presentation, right?
Yeah, I love it when I look at what computer scientists' websites.
Yeah.
they don't sort of make any allowances for humans.
For humans, but we are humans, Robert. Even computer scientists are humans. Yeah. But indeed, I know exactly what you mean. Right. Looking at another question. In the UK, local authorities are tasked with public health prevention. Do you envisage them using this tool? And is this something you would encourage in order to help design better interventions? So what do you think about the public health use case for this and people using this tool in that setting?
I think it's a bit, if I may say, it's a bit like ChatGPT. Yes, potentially, but I think with training and with caveats. I think that when I look at the results from this tool, I'm always looking at it through the lens of what I know and what I believe, of all the research that's been done and that I'm familiar with, and the systematic reviews and so on, so that I can do a sort of sense check on what it's doing. And so I think, because this is, if this was a perfect system, we could stop now. That would be the end of it. We just, okay, this is what you get, and it's a job done. But that's obviously not the case. So what I would say is, if you're not even if you are a stock smoking researcher, look at the outputs from it as a hypothesis, and then think, okay, how does that relate to what other information I've got? And we could try that out. So if I'm designing a digital intervention and I'm thinking, well, what BCTs would be worth putting in there? I can try things out and I say, okay, that actually looks like it makes sense to me. Let's try that. And then you may do some A/B testing or something like that. So yes, I think I definitely think that local authorities and others could benefit from it. And obviously we're producing a training program that I hope will help people to use it in a way that realizes that it's a tool to help them get a job done. It's not doing the job for them.
Yeah, no, that's a really important concept. And I think some of the intrinsic limitations, like the fact that it's based on published studies and some sort of interaction effects, may show up just depending on what has been studied, right? The system
yes.
isn't learning about the world, it's learning about what has been studied, right?
Really good point. We're predicting the outcome of studies with certain features. For example, most of the studies in the data set have an assumption about missing data, which is missing equals smoking. If you weren't able to follow them up and do biochemical verification, for example, then you assume they were smoking. Now that's going to depress the outcomes of the so inevitably they'll be lower than they would otherwise be. Other studies that are in the data set didn't do that. They took a different approach to missing values. So there's that. There's also the fact that we can know in this data set, we don't know what they actually put into the intervention. We only know what they reported. And we know that they don't report a lot of stuff that they actually did, and that it's different. The reporting bias is different in the intervention and control condition. So all we can say is if people reported using a problem-solving BCT in the intervention, then they got these better results. Now, for those people who are interested, again, because this is all open source, we have the data file with all of the text that was used to create these codes. And so people can see what did they mean by problem solving? What do they mean by things like adding objects to the environment or whatever it might be? What did that BCT actually look like? And would I necessarily agree that that's the right coding for it? The coding was pretty reliable, but you know, I would recommend doing that. Go and have a look. It's on the Open Science Framework, or is it on GitHub? I think it's on GitHub.
I think we'll have to, we'll put it on the Open Science Framework so that everything is available in the same place. Yeah.
So that's a really important point. This is like, all we can ever do is say what people have found when they've looked at stuff. And then you've somehow got to sort of extrapolate from that to what you think the truth is.
That's right. And just another really important point around this that I wanted not to lose was this fact that you may have unseen colliders, right? So you may have something annotated consistently in studies where the outcome was poorer, but it's not because of this thing that was annotated. It's because of some feature of the background setting or population or something, which then, brings. So it may be that you only used certain interventions in certain harder to reach populations, something like that. The system can learn about these interactions, but it can't learn about the underlying reality that it doesn't have data about.
And this is where I think, you know, as we move forward, we've got to expand the number of things that are coded by 400%, you know, and obviously add new studies. And what we want to really do, which we weren't good enough at doing, was to automate as much as possible of the information extraction process, so that it's not that massive job that, you know, it's taken us 6 years to code up, you know, these studies. So
so that was really hard. So some features worked and some features didn't work, and a partial annotation is not really sufficient to base an automated prediction on. And this was a kind of a hard learning of the project, wasn't it? One more, or perhaps we have time for 2 or 3 more questions, but the next one from Rachel Wood is, have you looked at any predictions for acceptability? Well, that's basically what you've been doing, Robert, haven't you? You've been sort of looking at and what do you think?
I think this is a project for someone. I think a student project even would be to, you know, a bit like you now having projects on ChatGPT and how to query it and interpret the results. You know, there's lots to mess around with here, where you would look at the predictions that it's making and sort of test them against what people think, you know, experts or non-experts, or even even in terms of acceptability, people with a view which may or not be evidence-based. So, for example, you'll notice in there that we don't have e-cigarettes. It's not actually because e-cigarettes aren't important, because they are. It's just that you need a pretty large number of studies, and although in meta-analyses, there are the studies, and the randomized trials do show, clear effectiveness of e-cigarettes. There's a Cochrane review about to come out which compares e-cigarettes with varenicline with other things, and the findings are very robust. But we don't have with this approach, we don't have the luxury of being able to say there was this study had 20,000 people in it and found this, and therefore this is probably true, because that's not what we're not interested in. That we're interested in making a prediction in new scenarios. So one study is one data point. It may have 100,000 people in it. It's still one data point. It just happens to be a data point that's quite accurately assessed. So we don't have the e-cigarette data. But if we did, and let's say, and this is a very interesting point, if we said, okay, it looks, the machine says e-cigarettes are a brilliant way of helping people stop smoking, half the smoking tobacco control community would go, that I don't believe that, because they don't think it's true. And so we have to think about how how we address issues of priors. What are people's priors? They may be right and the data may be wrong. The data may be right and they may be wrong. And we have to think about how we communicate the results in a way that allows everyone to get the benefit of these kinds of approaches to evidence synthesis.
Yeah, that's a really, really good point, because it's like there are different questions actually. And this approach can answer some questions, and it's targeting answering those types of questions. And then maybe some other approaches are needed to answer these different questions.
Yeah.
Yeah.
I think meta-analyses have still got some legs.
Still got some legs. Yes, exactly. So some combination. And of course, it would be really wonderful if these different perspectives on the sort of state-of-the-art latest evidence could be integrated and shown side by side, along with what they mean and what they say about this would be really helpful, I think. Our next question is
probably better be the last, I think.
Very good. Yes. Then last question. What general takeaways have you uncovered from this exercise about which types of interventions and combinations of interventions tend to be most effective in changing behavior? So I think we haven't done a systematic search of all combinations of features. Maybe you've got a kind of intuitive sense, Robert, from your experiences with the system.
Yeah, you can get the outcomes up to about 22-23%, which is about as good as anyone's ever been able to achieve. With a pretty representative sample. And with certain combinations. One of the interesting things is that certain BCTs seem to detract from success. You can try them out, when you get a chance. But
which again comes back to this question of which portions of the data set declared that those were used, right? So sometimes BCTs are overwhelmingly only declared in the control branch.
Yeah.
Because they're the standard of care, but that doesn't mean that they don't work. They do work. It's just that then no study shows that they work. So that's a possibility. I think that one of the mantras in smoking cessation has always been that the method that's likely to give you the best chance of success is a combination of face-to-face behavioral support, specialist behavioral support given by someone who knows what they're doing, and pharmacotherapy.
And that broadly is borne out in this data set. So,
Yeah.
you know, there isn't that's not a massive surprise. What's interesting, though, are what BCTs are coming out within that as ones that you maybe want to think about focusing on in your behavioral support. We don't have the granularity to tell you about specific ways of delivering, for example, cytosine or varenicline for 12 weeks versus 24 weeks. We don't have that granularity, but that's where you'd go to your meta-regressions and your meta-analyses. So it's kind of reassuring in a way that the broad brush principles seem to be borne out by this approach as well. And I think it gives some extra detail. What I think will happen as we explore this more will be whether we're seeing some patterns in relation to certain things working a bit better with some types of some groups than others. And I would treat those as hypotheses that you'd then want to explore.
That's right. That's right. So each kind of combination, which looks as though it's really working well in a prediction by this system, would be something which could be used to inform the design of a future study, right? You could say, oh, well, we could try this, but it's not hard data, obviously. Great. So thanks so much, Robert, for this really interesting discussion. Unfortunately, we were not able to get through all the questions, but rest assured that at some point we will go back to these questions that remained unanswered and post the answers on the Open Science Framework page. If you have any further questions that come to your mind now, please add them on this QR code scanned location. And next week, there will be a webinar on trust in artificial intelligence, another really interesting topic. And that will be at the same time, and I guess the same registration. Well, the registration information is available online. Save the date for the launch of the HPCP knowledge system on the 6th of June. So all the tools which we've been presenting in the last weeks, and including the prediction system, which we talked about today, will be launched officially for public consumers on the 6th of June. So that's really exciting, and I hope you're looking forward to that as much as we are. So that's the end of today's webinar, and here are some links if you want to follow or keep up with what's going on in the Human Behavior Change project. So see you again soon at a webinar in the future.